Yeah, Dev, should I start?
Yeah, I guess we can start now.
Okay, fine, we'll start. Yeah, so hi guys, I'm Rutvik. Today me and Srinivasan are here to present the session 5 of our summer school. The topic for today's session will be Intro to Deep Learning. We'll be dividing this into two parts. The first part will be taking it today and the other will be taken up on the Monday session. So we'll try to keep the session more interactive and let us ensure that you get the intuitive feel of the subject. We'll not go into the maths, rather we'll try to understand stuff more intuitively so that it makes much more sense and we get more better feel of the subject. So let's go ahead. So this is the table of contents. So the first thing that will be taken up is what is AI, what is AL, what is ML, what is DL. We often use them interchangeably without knowing what they exactly mean. So first let us try to understand what they are. After that, let us dive into what is deep learning, why deep learning, why is it more superior compared to the AI and ML, and then let's go into neural networks, try to understand its biological perspective, and then it is about the evolution of neural networks, how they have been evolving throughout these years. So yeah, first AI, ML, and deep learning, all these have been like the buzzwords which we have been popularly using around. We often use them interchangeably without exactly knowing what they mean. So AI, when we come to AI is a branch of computer science that deals with a wide range of capabilities of algorithms and techniques to simulate human intelligence. So it is like a broad spectrum, and we only deal with algorithms that represent or that help computers mimic human brain. So AI can be as simple as a combination of several if-else statements. For example, if you see how our human body functions, so if you're walking on a road, let us say, you see a car in front of you. So the first thing that the eyes send a message to the brain that, okay, there is a vehicle in front of you. So the brain sends a message to your legs to stop. If there is no vehicle in front of you, then the eyes send the message to the brain, and then the brain sends the message to the legs saying that you can move forward. So it is basically nothing but a simple if else statement. The same thing can be replicated for a robot which is moving on the road. That if something is in the way, if that is true, stop moving. If that is not true, continue moving ahead. So AI can be as simple as this. There are so many applications in our daily life of AI which we don't know. Like for example, the face recognition systems which are there, then the voice assistants which are there, the autonomous cars which are there. All these are nothing but a product of AI applications only. So within AI, machine learning is a subfield of AI. So our main intention is to mimic or imitate the human brain, and one such method is machine learning. In machine learning, what you basically do is we deal with algorithms that help mimic computers, the human brain, and these algorithms get better and better when they're exposed to more data sets. What that means is when we feed in more and more data, the algorithm learns on that data and it becomes more and more accurate. So the model will be able to predict the outcome in a more better way. So this training of machine learning involves optimization of several parameters, which we'll be discussing ahead. The main parameter will be how you will be reducing the error. So what do you mean by error? Now, when you're having the model will be predicting one outcome, and there will be some ground truth value, which is the actual outcome. Now you try to compare that ground truth value with what your model has predicted. That is the error. So if there is no, so what we have to do is we try to optimize this error or we try to minimize this error. And how we do this, that is what we basically deal with in machine learning. So there are various techniques in order to optimize these parameters. In the earlier sessions, we have already discussed several traditional methods like decision trees, SVM, naive Bayes classifiers, logistic regression, linear regression. All these are the methods of machine learning. But the point is, machine learning is a field that has been existing since the last 30, 40 years or from the 1960s itself. And deep learning is a subfield of machine learning, which is a very new and very young field of AI, which works basically on neural networks. So neural networks involves the use of multi-layered structures of algorithm. So the deep learning, when we are using the word deep, the deep refers to the depth of these neural networks. We'll try to understand about neural networks in great detail later on, but the main intention is to understand that neural networks have a lot of capabilities and it helps us do tasks which machine learning models cannot. So this is how a neural network looks like. We'll come back to this later on. Right now, so let us get a brief overview of what we have discussed now. So artificial intelligence is a broader spectrum which deals with all the algorithms that help computers mimic human intelligence. Within artificial intelligence, you have machine learning. Machine learning helps improve the computers, like it help the computers mimic human intelligence through algorithms which get better and better when they're exposed to more data. So it is like the algorithms learn on the data that we provide. Within machine learning, we have deep learning. Deep learning is mainly revolves about the use of neural networks, which we'll be discussing in greater detail later. So this is how a brief overview looks like. Do you guys have any doubts till now? Srinivasan, are there any doubts in the chat?
No. Yes, you can continue.
Okay, all right. So guys, if the pace is little fast, then you guys can stop me. How is the pace? Like, is this all right, or should I go a bit slower? You can drop in your feedback in the chat or with reactions. That will also work.
It's all right.
It's all right. Okay. Yeah. So the main question now comes is why deep learning and why not stick to the earlier methods, that is machine learning methods, which we have been discussing in the earlier sessions. So the earlier traditional methods which we discussed, like decision trees, SVM, naive-Bayes classifiers, logistic regression, all these algorithms are known as flat algorithms, which means these algorithms, they cannot directly process the raw data. There is a pre-processing step which is known as feature extraction. That is, so if you look at a diagram like this, in machine learning models, before the classification of the data, there is a pre-processing step which is feature extraction. But in the case of deep learning, this feature extraction and classification are taken place together. So there is no explicit need of having a separate pre-processing step. This makes things faster and they also make it much more user friendly. That is one of the major reasons why deep learning is more superior to machine learning. Apart from this, the other point is deep learning models, they tend to increase their accuracy with increasing amount of training data. This is not only true for deep learning models, this is also true for machine learning models, because the main base idea for machine learning models is how algorithms improve when they are exposed to more data sets. But the saturation point, if you see here, of traditional machine learning models is quite less. So the performance with the increase in data is less. So yeah, this is a plot of performance versus data. But if you see in the case of larger neural networks and these smaller neural networks, they have better saturation points. So with the increase in data, their performance is much more in comparison to the traditional machine learning methods. So these are the two major advantages which neural networks provide us in comparison to machine learning. And also, in general, the analogy of deep learning is that the rocket engine is the deep learning models and the fuel is the huge amounts of data we feed to these algorithms. So what it says is, like the models which we are developing, they are analogous to the rocket engine, and the amounts of data, the huge amount of data set that we give to our models is similar to the fuel of the rocket engine. So fuel in the sense, that's what. So the more data you give, the better your model will perform, because as it is exposed to more various data sets, it learns better, and as it learns better, it performs better. So it is somewhat similar to our humans only, which is like analogous to practice makes a man perfect. So the more you practice, the more you do, like the more you practice, the better you perform. So here also, the more it practices on newer data sets, the better it performs. I hope it's clear and intuitive till here. Any doubts till now? Yeah, so initially, I guess the session might be a little bit theoretical. Later on, we'll be looking into little bit of mathematical part, but let us keep that also intuitive and more interactive. I hope till now there are no doubts. If there are any doubts, you can pause me, you can interrupt in between and ask them.
Ritvik, I guess like somebody asked if you could go a little bit slower,
Okay.
and also like will you be sharing these slides? So for that, the slides have already been uploaded on the repo, so you can check out our GitHub repository and you'll find it there.
Yeah. Maybe we can also, just a second, I'll share both of those slides on our WhatsApp groups if they are not done yet. Yeah, I have shared those slides on the WhatsApp groups. You can look into that so that you can follow better. All right, we'll continue then. So till now, what we have understood is, let me brief it up then. We have discussed about what is AI, what is ML, and what is DL, how they all are apart, like different from each other, and what are the differences. What is deep learning and why is it more superior to machine learning? And then we have also discussed, that's what we have discussed till now. So basically, AI is the broader field. Machine learning is a subfield of AI, and deep learning is a subfield of machine learning. So this actually mainly briefs up everything till now. And why deep learning is superior to machine learning is because of this. You need not explicitly perform any pre-processing step, which has to be done in machine learning. So it makes it more user-friendly and faster. And also the performance versus data, we can see that the saturation point of neural networks is more. So the performance with data is much better compared to the traditional machine learning methods. So now let us see what are neural networks, and let us try to relate it with our biological neurons. Let us see how they are similar to them. Though there are several differences as well, let us try to relate or try to understand what are the common resemblances that will make us that will make it easier for us to understand how the neural networks function basically. So neural networks are also known as artificial neural networks, and they form the heart of our deep learning algorithms. So yeah, as I was mentioning earlier, if you see here, this is how our neural network looks like. So we have several hidden layers in between. We have one input layer where you will be giving in the input, and you'll be having one output layer where you will be getting the output. So the hidden layers are responsible for performing all these operations on the input data that we give. And these hidden layers only refer to the depth of deep learning. The deep refers to the depth of the hidden layers in these artificial neural networks. If you see this point, that's what it refers to. So now let us try to get a biological perspective of neural networks. See, so there are a lot of differences. The number of neurons in our human body is a lot more, and every neuron is again connected to thousands of other neurons, which is not the case of neural networks. But if we see the basic layered architecture, that somewhat resembles how neural networks function. So if you see how a simple brain works, you take an input from the environment, then you have this perception sense, which is something like the input layer. Then the message goes to your brain. So the brain is something like your processing layer or the hidden layer of neural networks. And then the message goes to the output, that is your output layer and the react, and then to the environment. So this sense is similar to our hidden input layer here. The processing layer is similar to this hidden layer here. and they react. Output is similar to the output layer here. So I guess you're able to understand that there is some resemblance between our normal neural networks and also the how the human brain, simple brain functions. So here also, if you observe it carefully, this is how a neural network looks like. This is a single neuron, and this is also a neuron. So the inputs are taken through the dendrites, which is similar to how inputs are taken here. This summation is a function that sums up all the inputs. And then you have F. F is known as the activation function. So what the activation function does is it takes this summation, okay, and it converts it into a suitable form, which will be passed on to the next neuron. So it basically activates. It will check whether the input has to be activated or not. We'll be discussing about activation functions in greater detail later on, but this use of activation function is also something that has been inspired from the biological neurons, because the researchers show that even dendrites apply a non-linear function on the input before it is being passed to the nucleus. That is what an activation function does even in the neural networks. We have several types of activation functions, which we'll be discussing later on, and we'll also understand its importance in the next few slides. So if you can see this, the basic framework of a neuron is somewhat similar to how it looks in the neuron of the neural network. So you can see that there are many resemblances. All right. So are things clear up to now? If there are any doubts or any questions which you have, you can unmute and ask, or you can drop in the chat box. We'll take it up. So mainly this biological perspective is to understand the inspiration or the motivation for why neural networks and how do they function. Now let us try to go through the evolution of neural networks, how they have been evolving throughout these years. As we have seen, this concept of AI has emerged in 1940s itself. So in these past 70, 80 years, there has been a lot of changes. There have been a lot of improvements which have been done. So let us try to understand how the progress has been. So if you see, the first neural network, mankind's first neural network is the McCulloch neuron. So it is a very simple network, neural network. So let us try to understand how it functions. So you can see that the neuron is divided into two parts. It has the G part and the F part. As we have seen here, yeah, here. So the G is the summation, and the F, which is the activation function. So G, what it does is it just takes the summation of the inputs. So let us say we are giving in some n inputs. So what it does is x1 plus x2 plus x3 till xn. And as it is a very basic model, it takes in only Boolean inputs, that is either 0 or 1. So it sums it up. The G, what it does is basically G of x is summation of xi from I equals to 1 to n. Now, this input will be sent on to the F, which is the activation function. And what it does is, so this activation function is known as a step function. So what the step function does is, if that summation is above a certain threshold, which is theta here, it will give the output as 1. If it is lesser than the threshold, it will give the output as 0. This threshold is known as, theta is known as thresholding parameter, which is something that we can fix. So whether that sum is greater than the threshold or not, depending upon that, you will be getting the output. This is known as a step function. So this step function, activation function, is not the most appropriate or the most efficient one, but as it has been one of the beginning stages, so it is just to get an idea about how activation functions work. So this decides whether the input has to be activated. If it is greater than the threshold, yes, the input has to be activated and we should get the output as 1. If not, it should be giving the output as 0. There are much more sophisticated activation functions like ReLU or sigmoid, which were discussed in the earlier sessions, I guess, and they will be discussed later on. Srinivasan will be taking up few of those in the upcoming in some while, and also some more will be discussed in the Monday session. So now let us try to understand this with a better example. Okay. So are you guys able to follow till here? I guess maybe after this example, you might understand things more clearly. So I'm taking this example being a cricket fan. I hope that many of you are able to relate. So what we are going to do is we are having an IPL match in the evening, and we have to decide whether you want to watch the match or not based on the McCulloch neuron. Now the inputs. Let us take three parameters. First parameter, let us say, is tomorrow a Sunday. The next will be, is the match between RCB and CSK. Let us suppose that it's the last match of Kohli and Dhoni. So it's a very crucial match. And the third factor, let us say, the third parameter is, can all friends watch the match together? Okay. So these are the three parameters which we are taking up. And now let us set our thresholding parameter. Thresholding parameter means our theta, which is here. Let us suppose that we set our thresholding parameter to 2. See, so this is completely up to us. We can fix it as 1, we can fix it as 0, we can fix it as 3. So at max it can be 3 because either one of them will be 0 or 1. So at max all of them will be 1, 1, 1, which is 3. That is the best possible case. But now let us set our parameter as 2. So what it basically means is x1 plus x2 plus x3. If it is greater than or equal to 2, the output will be 1. All right. If it is not, the output will be 0. If the output is 1, you're going to watch the match. If the output is 0, you won't watch the match. Do you guys understand this example? Okay. So now let us try to implement this. I have shared the Colab notebook on the WhatsApp groups. You can check it there. And it also has been uploaded on the GitHub repo. You can check it there as well. So I'll just run this else. So this is a very basic example. I haven't gone into great detail. I wanted to keep it more intuitive and less mathematical and less involved into the coding part. So let us try to interpret this table and draw some conclusions. Yeah, just a second. Right. So here, this is our data. Okay. We are having 8 people here. Then this is the data that whether they're watching RCB versus CSK match. Is it RCB versus CSK match? 1 is yes, 0 means no. Holiday tomorrow, 0 means no, yeah, 1 means yes. So this is a table which we are having, and this is the outcome. Okay. This is our ground truth. Ground truth in the sense we already know what is the outcome, but we'll try to predict based on these parameters what should be the outcome. So what we'll do is it's basically like we are not given the outcome and we only know these 4 parameters. Based on this, we'll just try to we'll try to figure out, or we'll just try to make some mathematical relation and identify. We have to basically guess whether they'll be watching the match or not, and it will be a mathematical guess. That's what we are basically doing here. So as we have discussed earlier, this is one definition, that is your step function. I have defined it here. I have defined our neuron, how it functions, and then we are trying to calculate the error. Let's try to understand this code. It's a very simple code. So first, I'm defining this function as step. As we have seen, what is our step? Step is our activation function. So if the sum is greater than or equals to threshold, it should return 1, or else it will be returning 0. That is our step function. Now let us go to our neuron. What it does is, initially let us initiate sum to 0. What does our neuron do? It will take the inputs, it will sum them up, and then we'll apply our step function over that. So that's what we are doing here. Sum equals to sum plus, yeah. So df is our data frame. Df is our data frame. Lock j is location j, and IAT means I. So j is our index of the row, I is the index of the column. So what we are trying to do is we are fixing our j. So fixing j is in the sense, let us fix one person, and then we are varying our I from 1 to 5. So let us say, let us fix it Aditya. And then we are varying the I. So we get 0, we get 1, we get 0, we get 1, we get 0. And that is only till 5. So as you might have, like in the earlier sessions, we have discussed that if it is 5, 5 will not be taken into, it will not be included. So it is basically like 1 comma 4 closed. So 5 will not be taken up. You guys understand that, right? So now what we are doing is we are just summing up all those parameters. So 0 plus 1 plus 0 plus 0, we are doing that. And then we are returning step sum. So step is it goes here. Then we just plug in our sum, whatever we got here. We'll plug it in here. If that sum is greater than threshold, return 1. If it is not greater, return 0. So this is basically our our McCulloch Pitts neuron. Did you guys understand this code till here? Or should I repeat it again?
Understood.
They understood. Okay, please. Right. So now after this, what we are trying to do is this basically gives us what is the predicted output. So applying this function will basically give us what is our predicted output. But that is not the only thing that we want. We want to find out the error as well. What do you mean by error? As I already told, error is basically what is the ground truth value and what is your predicted value. You will compare those both. And here there are again several types of errors. So there are several types, but we'll be discussing mainly about mean squared error. Mean squared error is basically that you find out the difference, you square it up, and you find the mean of that square. So that's what we are doing here if you observe carefully. So see, now this time we are varying j. Why are we varying j? Because this is we want to find out we know the predicted output of 0. Now what we are doing is we are trying to find the error for each one of them, square them up and add them and divide by the total value. So that is why here our varying index will be j. In the initial function, our varying index will be I, because you want to vary over these parameters. Now you want to vary over the number of people. So you get that, right? So that's what we have done here. Predicted output is MP neuron j. Actual output is df log j I85. Why 5? So 0, 1, 2, 3, 4, 5. So 5 is our this one. And j I kept it as a variable because for each j you'll be checking, like when j equals to 0, it is 1. So you'll compare it with the predicted output. You'll subtract that, square that, add it up. Similarly 0, 1, 0. That's what you're doing. If you observe here, so the error is error plus MP neuron minus this one square. So you're just adding up all the errors, and then finally you're defining mean squared error as error by 8. That is because you're having total 8 values. You get this, right? So this is what we have done. Now let us try to observe. Let us play around with this first of all. I have set the threshold as 3, but as I told earlier, threshold is something that we can set on our own. There is no harm there. So let us start with 0. Okay. Before starting, let us try to understand. Like for example, yeah, in the first one, let us see. When we are putting threshold as 0, it says predicted output is 1. Let us try to understand why. So in the first case, Ravi, 1, 0, 1, 0. So what is the sum of the inputs? 1 plus 0 plus 1 plus 0, that is 2. And what is our threshold? Threshold is 0. Sum 2 is greater than 0, so it will return as 1. So therefore, our predicted output is 1. What is our actual output? This is our actual output. This is our actual output. So that shows it is 0. So in this case, our predicted and actual both are matching, which means that there is no error here. Let us go to the next case. Rahul, so here it says that can join in. Okay, so there is only 1 here. Rest all are zeros, right? 0 plus 0 plus 0 plus 0 plus 1. So that is 1. And again, you come here. Sum is 1. Sum is greater than 0, which means that it will again return 1. So our predicted outcome for the second case is also 1, but in actuality it is 0. The actual outcome is 0, but our predicted outcome is 1. So you see this, right? Similarly, we have performed for the remaining 6 persons. So if you notice here, there is an error 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 here. So we have 4 errors. So the mean squared error will be 4 by 8, that is 0.5. Okay. Now let us try to increase the threshold and see what happens. When the threshold is 1, also we can again perform the similar task, and you can again see that in the similar way how we have discussed earlier. Let us do the same thing. I'll show it once again how we are doing it. Predicted outcome. So yeah, sum is 1 plus 1, that is 2. 2 is greater than our threshold 1, so it should return 1. So therefore our predicted outcome is 1 and the actual outcome is also 1, which is fine. There is no error. But if you see in the next case, for Rahul, can friends join in is 1, which is greater than or equals to means yes, true, it is equal to 1. So again it will return 1, but the actual outcome is 1, 0. So you can see that predicted outcome is 1, actual outcome is 0. So there is an error again. So similarly, if you compare for the rest, there is an error here, there is an error here, there is an error here, there is an error here. So you're having again 4 errors. So 4 by 8.5. Now let us increase the threshold again to 2. Let's see what happens when it is 2. So yeah, so if you observe here, the mean squared error has decreased. That is because if you see in the first case, okay, it is fine. Let us come to second case. So in the second case, 0 plus 0 plus 0 plus 1, that is 1. Is 1 greater than or equals to 2? No, it is not. So it will return 0. So our predicted outcome is 0 and even our actual outcome is 0. So that is what is happening here, and it shows that there is no error here. Similarly, we are performing for the others. So there is an error here if you observe, and there is an error here if you observe. So the mean square error is 2 divided by 8.25. Let us try to increase it to 3 and see what happens. So when it is 3, so you can see here, initially in the first 3 cases when it was 0, 1, 2, we have observed that the predicted outcome and actual outcome were both 1. But here it says predicted outcome is 0. So if you notice here, that is because 1 plus 1 is 2. 2 is not greater than or equals to 3. So it will return 0. But the actual outcome is 1. That is what is happening here. So I guess you got a fair idea what is actually happening. So if you notice carefully, what has actually happened is when the threshold was 0, what was our mean squared error? It was 0.5. When the threshold is 1, what is our mean square error? It is again 0.5. When it is 2, the mean square error has decreased to 0.25. And when the threshold is 3, it has again increased to 0.375. So the sweet spot is when threshold is 2. When threshold is 2, you're having the least error. And so basically what is happening is, if you observe carefully, what we can conclude from here is, when the threshold is 0, the condition is not strong. It is not strong enough. So therefore, every time the predicted outcome is coming out to be 1, which is something that we don't want, which is also the case when the threshold is 1. But if we put the threshold as 3, the condition is too strong, due to which the predicted outcome is most of the time 0, which is again something that we don't want. So we want a right balance between these both. And that is possible only when we are having our threshold to be 2. So if you see, when the threshold is 2, there are ones, there are zeros. So it is the proper balance. That is the reason why we are getting the least error in this case. Did you guys understand this? A thumbs up or anything will work.
I have a gentle doubt.
Okay.
So, is the method actually a trial and error for a threshold, or do we have an algorithm of going through all the one
Yeah.
outcomes and then checking the value, like the sum
Yeah. Yeah.
ideal
That's a
threshold
very
sum?
good doubt. Yeah, right. I'll be discussing that in a while. That's a good question. So basically, in order to show how it basically works, or to get the intuitive feel, I have done this manually. But obviously, this won't be the case for uh, when the data are very large, when the data sets are very large, this is not possible. You can't manually check everything. So there are algorithms which will try to optimize the threshold value, which will try to optimize all these parameters in such a way that the error will be minimized. So there are algorithms related to that. That is what we'll be dealing with later on. I hope that
Okay.
clears it out.
Yeah.
Yeah, this is just to give a feel that how the threshold functions and how the mean square error varies by changing the threshold. So is this part clear, or should I go through anything again? Okay, what do you mean by okay, fine? Yeah. Well, yeah, what Kunal told is right. It returns the data at I. Okay, the slides have been shared. Okay, I don't think there is any major concern. The pace is fine, right? Or should I go a little bit slower?
Fine, sir.
Yeah, you
Thank you.
say it's fine.
No problem.
Okay, please. Okay, fine. Now, yeah, so keep interrupting me in between. If you have doubts, do ask. Okay, that will ensure that we have better interaction and the class will be more interesting. It shouldn't be one-sided. It shouldn't be monologuous. So try to ensure that you also like, yeah, you can drop down any doubt with whatever you have in the chat box, or you can unmute and ask me in between. Even though if you feel that the pace is little fast, you can unmute and stop me in between so that I get a little slower. Okay, yeah, so let us now make some more observations in our data. So if you observe here, when friends join in, that is the only parameter that is on and rest all are 0. Okay, we see that the outcome is 0. We are just analyzing our data. Okay, when there is a holiday tomorrow, but rest all parameters are 0, which means tomorrow is some KKR versus Punjab match, or the match is in the afternoon and friends are having some maths exam or something. So this is the only thing that is in your favor, that is you are having a holiday tomorrow, but rest all are not in your favor, then also the outcome is 0. The same thing happens here. When the match is in the evening, but rest all parameters are not in your favor, the outcome is 0. But if you come here, if the match is between RCB and CSK, if the match is between Kohli and Dhoni, then you don't care whether you have a holiday tomorrow. You don't care whether you have the match in the afternoon or in the evening. You don't care whether your friends will join in or not. You just want to see Dhoni and Kohli batting and playing against each other. So the outcome is 1. So can you guys conclude anything? Can you make any relation
RCB
between?
and CSK match overrides all parameters.
Can you come again? Yeah, I feel you are moving in the right
The
direction. Can
match
you come
between
again?
RCB and CSK will overrides all the other parameters.
Yeah, exactly. Perfect. So what is the thing that we can observe is this parameter has more influence on our final outcome in comparison to the other parameters. Like if you're having friends joining it, your outcome is 0. But if you're having a holiday tomorrow, still your outcome is 0. But if you're having only RCB CSK match and other 3 parameters are 0, still your outcome is 1. So this is something that is not taken care in the case of McCulloch neuron. What it basically does is it gives equal value or equal weightage to all the parameters, which need not be the case always. Like in this example, RCB CSK match is something that has more weightage compared to the other parameters, which is not being taken care of by the McCulloch neuron. And this is one of the drawbacks of McCulloch neuron, which we'll be discussing now. So I guess this code is clear and you understand how a basic McCulloch neuron works. Let us now discuss about what are the issues that we have. Yeah. So before going to that, another thing which I wanted to cover is since the input. So now we have seen that in McCulloch neuron, the input and the output is either 0 or 1. So they are Boolean values. So that's why McCulloch neurons can also represent Boolean functions. And how do you ensure that is by setting up the right thresholding parameter. So Boolean functions are your AND function, OR function, NOR function. These you might be coming across in semiconductors in class 12 when we might be studying the logic gates. This is very much similar to that. So what happens in an AND gate? AND gate is basically like when both the inputs are on, then only the output is on. In OR, if either one of them is on, the output is on. NOR is like the negation of OR. So here if you see x1 plus x2 plus x3, as we have seen, AND function is basically when all the three inputs are on, which means all the three have to be 1, which means the input has to be 3. I've just put greater than because that is anyways not possible. So that is something that we need not be worried about. Greater than or equals to 3 will work because the maximum summation will be 3 since their domain is either 0 or 1. Right? So this is basically like how we are able to set the thresholding parameter. Here our thresholding parameter is 3. In the case of OR function, if any one of them is on, the output will be 1. So basically it is like if any one of them is 1. So therefore the summation should be greater than or equals to 1. And in NOR, it is just the opposite of this. So when both are switched off, then only you will be getting the output as 1. So therefore g of x should be equals to 0. So basically the idea is how do you choose the thresholding parameter? In AND, the thresholding parameter is all of them have to be switched on. So it should be 3. In OR, either one of them should be switched on. So it is 1. Here, both of them should be switched off. So it should be 0. In a similar way, we can also, what we can do is other Boolean functions can also be defined. But the key idea is how you choose the right thresholding parameter. Is this clear? This is just a basic application of McCulloch's neuron, which I wanted to cover. The other gates also you can try kind of work it on yourself. The basic idea remains the same, that how you choose your thresholding parameter. So yeah, now coming to the limitations. The first limitation is, as you see here, what about non-Boolean inputs? That is, till now we have been discussing about when the input is either 0 or 1, which need not be the case always. So what to do if the input is not a non-Boolean value? That is, what if it is 0.5 or what if it is 4.8, something like that. Next, do we need to hand code the threshold? This was one question, valid question, which was asked by someone right now, like some time back, that do we manually change or is there any algorithm? So this is one of the drawback of McCulloch's neuron. That is, you are like doing it manually, which is not the case or which may not be possible all the time. And third, very importantly, as we have seen now, are all inputs equal? What if we want to assign more importance? Like in our data set now, CSK versus RCB match has much more weightage compared to the other parameters. So if there is a similar case like that, how do we handle such cases? Because McCulloch's neuron does not take into account of such things because it gives equal importance to all the parameters. So these are the 3 limitations which we are having in McCulloch's neuron that we want to kind of rectify in the upcoming neurons which are there. So this is the beginning step, you can say. And the next neural network that has developed is Perceptrons. So Perceptron is, you can say, the second stage of this evolution. And it tried to resolve one of these major drawbacks which was faced by McCulloch's neuron, that all inputs are they equally important. So they are not. So if they are not, how do we take that into account? That is what is the issue that is resolved by Perceptrons. I'll just stop here for 2-3 minutes. Are you guys like clear till here, or is there any doubt? If there are no doubts, I guess we can continue. If you have any doubts, you can unmute and ask. Yeah, let me check the chat. Okay, right. Okay, I don't see any doubts. So then maybe we'll continue. Yeah. So let us try to understand this, how this major drawback has been resolved. This has been resolved by introducing this concept called as weight. Okay. So weights are nothing but they are some integer values which are multiplied with the input before they are summed up. So generally it used to be like x1 plus x2 plus x3, but this time we don't do that. Rather we multiply it with some factor called w and then we sum it up. So it is like w1 x1 plus w2 x2 plus w3 x3. We sum that up and then we add a term which is called as bias, and then we have our step function which is like if the summation wixi plus bias term, if it is greater than or equals to 0, fire the output as 1 or else fire the output as 0. That's what it says. So the only major difference that you see here is summation of wx. Now few of you might be wondering what bias is. So let us try to understand bias now. See, so bias is basically like if you just go back. Yeah, so if you see here, what have we done? Gx is nothing but summation of xi that is greater than or equals to theta. What we'll do now is just bring this theta towards the LHS. So it becomes minus theta. So g of x minus theta is greater than or equals to 0. Basically what we are doing is that minus theta, whichever is there, that we are defining it as some plus b, which is our bias term. Did you guys understand that? So bias is nothing new. It is the same thing that we have been coming across earlier. That is, it is nothing but the negative of the threshold value. You have just modified the equation a little bit, but the base remains the same. You have just interchanged the terms, or you brought the term from the RHS to the LHS and you have defined it by some new variable. That's all. So the major change that you observe here is you are multiplying a factor called W, which is the weight, which will take into account of the fact that not all inputs are equally important. There are few inputs which have more weightage and in comparison to the others. Okay, so let us see what are the basic steps. The steps remain the same. Multiply all inputs by W, sum them up. Okay, then the bias term is added to the weighted sum. Correct. So basically it is like the weights deal with scaling the input because you are multiplying the term, and the bias deals with shifting the input. This is to understand the point mathematically. Intuitively, if you want to understand, you can understand bias as your threshold, negative of threshold, and the weighted sum is nothing but the weight has been multiplied to take into account of the importance of each input that is given. And then you add the sums together, so you get a weighted sum here. So the weighted sum plus bias greater than or equals to 0 gives you output as 1, less than will give you output as 0. That is your activation function, which is your step function. Did you guys understand how a perceptron works?
Yes, sir.
Yeah, it's clear, right? Now what we'll try to do is let us try to understand this better by applying this perceptron concept on our data set. Okay, so we have seen that RCB CSK was something that we have observed that has more weightage, due to which we are not taking into consideration. So now let us apply the perceptron model onto our data set and see how the output is. Okay. So one thing which I want to mention is all this I'm doing it manually here in order to show how things work, in order to give you an intuitive feel. Mathematically, there are algorithms which have been discussed earlier and which will be also being discussed in the Monday session called gradient descent, backpropagation. These are some algorithms which are there, which are more mathematically involved. So these algorithms, they take care of how the parameters, that is threshold, how the weights, how they have to be iterated in such a way that we get the best outcome, that is the optimum or the minimized mean square error. So there are parameters like that. There are algorithms like that which handle all these. So we need not do them manually. I'm doing it manually here to just give you a feel of how actually the neural networks work. So I hope that is clear. So now let us do the same thing. I'm keeping the threshold as 3 here. And now here I'm like defining the weights. Okay. So as we have seen, RCB CSK match has the most weightage. So I have given it a greater input. I have assigned a larger value for that. And the others, I have just randomly put some values. As I have shared the Google Colab notebook with you guys, what you can do is you can just copy it to a drive and you can play around. You can change the weights however you want. You can change the threshold however you want. And you can try to observe how the error is changing. That is something you are free to do. That will give you a better idea of how the neural networks are working. So here, as we have observed that CSK and RCB match has more weightage, I have assigned a larger value here. Okay. And then the others, I have just randomly put some values. And now the same thing I have done again. Define step weighted sum. So if the weighted sum is greater than the threshold, that is, it will be returning 1, or else it will return 0. And then we have definition of perceptron here. That is, I'm again doing the weighted sum. So basically here, this additional term will come. That is, I'm just multiplying the weights. I'm multiplying the weight with the corresponding input, and I'm just summing it up. So finally, the returning function will be step of weighted sum. Step will be going up here. You plug in the weighted sum here. Check if it is greater than threshold. If yes, output is 1. If no, output is 0. That's how it works. And then I'm just finding out the error. The error concept remains the same. Actual value minus the predicted value square. I'm summing that up and dividing it by 8 to get the mean. Okay. The code is clear, right? There is no much. Yeah. Go ahead.
How did we get the array of weights?
Yeah, so the array of weights I have defined it here. This is what I have done manually. That's what I have been telling. As we have observed
like
that
it's done from trial and error. Like it is the best possible setup or something like that.
Yeah, correct. That's what I have done. Like, see, in actually what happens is we are having these algorithms which try to ensure that we get the best weights and the best threshold. That is the optimum weight and threshold for which our error is least. That's how the actual neural networks work. But in order to make it more clear and more easy to understand, I have manually like set up these weights here, and I have set up the threshold here. So this is something I'm doing it manually to show you how actually the mechanism works. But in reality, what happens is in neural networks, there are algorithms which are solely devoted to this purpose, that is iterating or updating the weights and threshold in such a way that the mean square error is minimized. This is something that I have done by trial and error. Not even trial and error, you can say that what we have seen is, since RCB CSK match is having more weightage, I just put a 3 here. And as the other parameters are not very important, I have just changed them here. Like, see, it was initially 2 1 1. I'll change it to 1 2 1. It doesn't matter. I just the only thing that we have observed is RCB CSK match has more weightage. So just ensure that you put a higher value for that, and the remaining are almost the same. You got it, right? Or should I explain it again?
Yes, got it.
Okay, right. Is the code part clear? There is no change in the code. Basically, I'm just multiplying this extra weights term. That's the only difference. The remaining stuff remains the same. This step function concept remains the same. Okay, sorry. Yeah, step function concept remains the same. Only this definition changes here. The error concept again remains the same. So the only change happens is you're multiplying an additional weight term with every input and you're summing it up. That is why it is the weighted sum. Okay. Now let us try to see what happens. Let us try to understand this. Yeah, let us take this example there. The predicted output is 1. Let us see how it comes. So it is 3 1 2 1. Okay, just keep that in mind. Just a second. Yeah, so 3 1 2 1. Let us go up here. CSK 1 is there. So let us multiply that 3 with 1. So 3 into 1 plus 1 into 0 plus 2 into 1 plus 1 into 0. So it is 2 plus 3, 5. So our output which is coming is 5. Then that weighted sum is 5. So it will go into the step function. Is the weighted sum greater than threshold? Yes, 5 is greater than or equals to 3. That is true. So it will return 1, or else it will return 0. So it is going to return 1 here. So our predicted output is 1. Actual output is also 1. Now let us come to the other case. So in the second case, what is happening is all these parameters are 0 except the last one, and the corresponding weight is 1 here. So 1 multiplied by 1. Okay, 1 multiplied by 1. Is that greater than the threshold? Just come here and check. Is 1 greater than 3? No, it is not. So it will return 0. For example, let us change the weight here also as 3. I'm just showing it here to give you an idea. Now what will happen? 3 will get multiplied with 1. So 3 into 1 is 3. 3 is equals to 3. So the step function should fire the return as 1, which is happening here. So you can see here output is 1, but in the actual output is 0. So you can see that, right? Did you guys understand this? So by simply changing the weight, I'm able to change the predicted output. Is that clear?
Clear, sir.
Okay, yeah. Now, yeah, okay, fine. So that's what it is doing. So if you see here 1 1 0 0 1 1 0 0 0 0. Okay, so there is an error here 1 0, and there is also an error here that is 0 1. Let us try to see what is the error here. So here the actual output is 0. That is in the third last case. Okay, Rohit. So it is evening match 1. 1 will get multiplied by 2. So 2 comes there. Plus 1 multiplied by 1, that is 3. So 3 is equal to the threshold 3. So therefore the outcome is 1, but the actual outcome is 0. So let us make a small change here and observe it. So let us change the parameter, something like this. Let's make this 2 and let's make this 1. This I'm just doing on trial and error basis only. Now let us see the third case. Yeah. So now if you see that the predicted output is 0 and the actual output is 0. That is because I have changed the weight that is corresponding to evening match. So evening match weight was initially 2. So 2 plus 1 was 3, and hence it was firing a 1. But now I have changed that weight to 1. So it is 1 into 1 plus 1 into 1, that is 2. 2 is less than 3. So the predicted outcome is 0. Actual outcome is also 0. So you can see that it is perfectly matching here. So there is no error here, basically, if you see. And most importantly, if you observe the last case, initially we used to say that threshold is 2, threshold is 3, and only 1 is not enough. But now as we have multiplied it 3, 1 into 3 is 3, and hence even though this is the single parameter, as it is having more weightage, so it is equivalent to having the value of 3. 1 into 3 is 3, and 3 equals to 3. So our predicted outcome is same as the actual outcome. So if you observe, when the threshold is 3 here, what was our error? I guess it was 0.375. Let us check again. Yeah, 0.375. But if the threshold, but for the same threshold here, by introducing this concept of weights, you can see our error is 0. So we can choose the suitable weights in such a way that we get the least error, and hence weights can help the neural networks or can help the perceptrons have better accuracy than in comparison to the one without weights. So I just want to emphasize on the fact that weights are something which has to be taken into consideration, so that all the inputs are not having the same value and some inputs have greater influence. That is something we have to take into consideration, which we have taken in this case, due to which our error has been minimized. It is 0 here. Did you guys understand this part? Did you get the intuitive feel? That's what I want to like primarily ask about. You can see that by introducing weights, we are able to minimize the error from what it was earlier. So definitely weights are something that have an added advantage and help our models to perform better on the data. Did you guys understand that? Or is there any part where I have to like explain again? Let me check this chat. Any reaction will work. If you're able to understand, a thumbs up would be great. Are you guys still able to follow, or is there anything which I have to go through again?
I have one doubt.
Yeah. Go ahead.
The zero in the table indicates that there is no relation with uh, that particular variable. Like if it is there or not, it is not important for that particular person.
Okay. Yeah, right. Okay, you mean if what does weight equals to 0 imply? That's what you mean, right?
No, wait. In the data table zero. What does zero indicate?
Okay, fine. You mean here what does 0 imply? 0 is no. 0 is no. 1 is yes. See, basically RCB versus CSK match, 1 means yes, there is RCB versus CSK match. 0 means no, there is no RCB versus CSK match.
Okay, cool.
It is like your general Boolean function. 1 means yes, 0 means no. Evening match, 1 means yes, 0 means no, it's not an evening match, it's an afternoon match.
Okay.
Yeah, is that clear now?
Yeah.
Yeah, and outcome 1 means you're going to watch the match. Outcome 0 means you're not going to watch the match.
Okay, got it.
Yeah. Any other doubts? See, if you're not asking doubts, it either means that you have understood everything or you haven't understood anything. I hope it's the first case. If there is any other doubt, you can go ahead, or else we'll take a short break for 5 minutes so that Srinivasan can move ahead. Yeah, before that, let me just try to go through some of the stuff which I have. So yeah, we have basically worked upon this example. We have used the same data set and we try to understand how weights are better off and how they help the models learn better. Okay. Now, what is the other drawback that we are having? So other drawback is about the activation function. So if you observe here, the major drawback is that activation function is a basic step function. That is, it is either 0 or 1. And that is not something that we want all the time. So it is not the best or the most sophisticated activation function. So there are a lot more other activation functions like sigmoid function, tanh function, relu. These are other activation functions which are more better as they give better outcomes. That Srinivasan will be discussing that ahead. Okay, so this is one of the major drawback which is there. Apart from that, the other and also the Boolean data which is there. We have seen that the Boolean input which was there in the case of perceptrons also it is either 0 or 1, which is not something that we want all the time. So this is one drawback that is still to be rectified. But the issue of are all inputs equal is something that has been cleared by introducing this concept of weights and multiplying the weights with the corresponding inputs. We are trying to ensure that the inputs which are having more influence, they have a greater say in the final outcome. And yeah, so right now what we have discussed is only a single perceptron. This is a single layer perceptron, you can say. This is a multi-layer perceptron. This looks complicated, but the basic idea remains the same. Okay, so it takes input from here, it gives output. So there are several layers. The main mechanism remains the same. Every single perceptron functions as what we have been discussing till now, that it takes wx summation plus b if it is greater than or equals to 0, 1 or else 0. So this is how a multi-layer perceptron looks like. And from this, it has evolved to our current neural network. This is how our current neural network looks like. So we have an input layer, we have hidden layers, we have output layer as we have discussed earlier. So in the modern neural network, all the three drawbacks which we have mentioned earlier. One, that is input has to be Boolean function that is resolved in our modern day neural network. It can be any input. It need not be either 0 or 1 only. It can take any input, any real value. Then you have the weights which will take care of the inputs, like the weightage of the inputs. And also the other factor which is there. What was the other one that we have seen? That is, yeah, the activation function. So the activation function issue, if you see here, uh, the current day model, the modern neural networks which are there, they use these activation functions like sigmoid, tanh, relu, which are much more sophisticated, and they also ensure that the output is not just 0 or 1, rather it is any value between 0 or 1, or it can take any real value. So the modern day neural network ensures that all the drawbacks that we have mentioned earlier are cleared. So this is like the most advanced neural network that we are having right now. So you can see how it has evolved. It has evolved from a very basic input 0 or 1 Boolean function input to a model where it has taken into consideration of the weights. Then it has evolved to what it is today, where it takes in any real value, gives out any real value, and also achieves a very great accuracy. Yeah, so that's it from my side. Do you guys have any doubts? I hope I wasn't too fast. I tried to keep it less mathematical and try to ensure that you guys will be able to follow. I hope that you guys get the intuitive feel of whatever is happening. That is something that is very important. And I recommend you guys or suggest you guys not to get intimidated with these large codes and the huge mathematical derivations or whatever capable, like whatever mathematical stuff that is involved. It is very important that you first get the intuitive feel and start liking the subject. So once you start liking the subject, then you can get into that, and eventually you will find it easier to understand all the more rigorous part. So initially, to begin with, it is important that you have a proper motivation to move ahead, and that motivation is something that you get when you understand things more intuitively. We'll stop here. We'll take 5 minutes break. After that, Srinivasan will be continuing. He'll be discussing about neural networks in some greater detail. So yeah, I hope you guys enjoyed the session and you have understood the stuff. So everything is clear, right?
Clear. Thank you, sir.
Yeah, thank you. Fine, we'll take. Oh, okay, so there's a doubt. Yeah, what is the purpose of sophisticated activation function, right? So the main reason is, if you observe here, yeah, that's a good doubt. So see here, when you're having a step function, your output is only 0 or 1. That is not the case all the time. And also, when you're having more complex data sets, it is important that your model should be able to mimic those models, should be able to mimic those data sets in a more better way. And in order to ensure that happens, you need to have more sophisticated activation functions. So when I say sophisticated, it means functions which are not just linear, and they also have some non-linearity involved. Like activation function sigmoid is 1 divided by 1 plus e power minus x. So all these activation functions, what they do is they ensure that the data is not just a linear combination, because if you see here, everything is linearly related, like w1 x1 plus wx w2 x2 plus w3 x3 and so on. So that is a linear combination. You don't want the function to be always linear. Ensuring that it is non-linear will help you will help the model to better mimic the final outcome, and you get better accuracy. So in order to ensure that happens, you need to have an activation function which is non-linear in nature, which takes care of the fact that models are able to replicate more complex data sets. Okay, great. Fine, then we'll take a 5 minutes break. We'll start at 12. Okay, so that is 3:20. Yeah, we'll start at 3:20. Srinivasan, that's fine, right?
Yeah.
Okay, bro. Fine.
Hello. Yeah. I hope I'm audible. Just checking now.
Yeah, you're audible.
Okay. Okay, hello. I hope I'm audible. And can you guys see my screen?
Yeah, yeah.
Okay. So shall we start?
Yeah, we can begin, I guess.
Okay. Okay. So I'm Srinivasan, and I'll be talking a little bit more about neural networks. Specifically, I'll be showing you guys how you can code a neural network from scratch, right? A simple neural network from scratch. So let's begin. All right. So So this is basically, so I made this small presentation. It's basically more of an introduction, or compilation, you could say, of the things I'll be using. So this is what this presentation has as the parts of the code in a neural network. A little bit on what cost or loss function is, activation, and compilation of the PyTorch functions that I'll be using. So PyTorch, as you might know, is a famous library. It's used a lot in machine learning and deep learning, and I'll be using PyTorch to develop the neural network that we'll be building today. So, and yeah, sorry about the page numbers. I guess the page numbers are kind of off, so you can know that. So parts of a neural network. So we have the initialization, where we'll be initializing the weight, the weights, biases. Initializing weights, biases, true values, etc. So I show all of that in code, so don't worry about this. Then we have a forward pass, which is basically where we calculate the output of the layer. Okay, so that's called forward pass basically. And then we have a loss function that I'll be talking about a little more in detail. We have what's called a back propagation step. Again, I'll be taking this up. And then there's a new forward pass so that we can actually compare the two and we see how the output changes. Okay, so let's get into it. Um, okay, right. Right. So let's start with imports. So as I said, we'll be using PyTorch. So PyTorch, as I said, is a library that offers what is called a tensor capability. So what is a tensor? It's basically like an array. Like if you guys remember the NumPy array, it's like a NumPy array, except in PyTorch it's called a tensor. And PyTorch has a lot of inbuilt functions that directly operate on these tensors. So you don't have to pick up each number and do it manually. It's much easier using PyTorch. So we'll be using PyTorch throughout this. So you call it using import torch. Oh, let's give it a second. Nearly there. Okay, right. So there it is. We imported PyTorch. Okay, so now let's have a look at what the network is. So if you remember from what Ritvik told you a few minutes back, what's a neural network? It's basically a structure that has an input layer, what's called hidden layers, and then there's an output layer, correct? And also, yes, before I go any further, is this font size fine or should I zoom in a bit? Can somebody please give me a heads up on that?
It's
I
fine.
guess it is fine. Yeah.
Okay, cool. So yeah, so we have an input layer, we have an output layer, and all the layers in between are called hidden layers. So what's special in a neural network is, so each one of these circles basically represents a neuron, right? So our input layer as such is, I've represented it in red. So this layer basically has two neurons. Same way, there are two hidden layers here, as you can see. One is in blue and one is in orange, and each of them has three neurons. And then we have a yellow layer, which is the output layer, which has only one neuron. Okay, so basically, the whole network as a whole is giving me one output. That is the most important thing, because whatever function this network is performing, whatever prediction it's making, comes out of here, right? This yellow unit. So I'll be coming back to this every now and then. So I've got a screenshot of this here. So yeah, keep note of which color represents which layer. Otherwise, we keep coming back to it, so it doesn't matter. So in a neural network, you can see that in two subsequent layers, right, in two adjacent layers, all the neurons are connected. So you see this red neuron here is connected to this, this, and this in the adjacent layer, right? So each neuron is fully connected. So this is called a fully connected layer. And there are actually different types of layers that you'll encounter more as we, in later sessions. But for now, we're coding the basic neural network. So for us, every neuron is connected to every other neuron in the adjacent layer. Okay. So the network has four layers: input, two hidden, and an output layer. And as Ritvik told you about activation function, so just don't worry about this line here. We'll come back to exactly what this means. But we'll be using what's called radio activation for these three layers and sigmoid for this layer. So I'll come back to what this means in a bit. So don't worry about that. And we will refer to each layer by the color. Okay. So everywhere in the code, when we're talking about the input layer, it will be red. These two layers will be blue and orange, and the output layer will be yellow. Okay. So which is the output that we care about? Yellow. And which is the input that we give? It's red. Right. Okay. So we'll be coming to the first part, weights and biases. So now if you remember the difference between a McCulloch neuron and a perceptron, it was what was called the weights, right? So what do these weights do? It basically gives you an idea of how important each different parameter is, right? So for example, suppose this neuron is giving me some parameter A and this is giving me some parameter B, right? So they're just two different parameters. Now I know that one of them could easily be more important than the other. For example, in the IPL example, continuing in the IPL example you saw today, suppose the upper neuron, sorry, suppose the upper neuron is what gives you whether it's raining, and the lower neuron is what gives you whether it's an RCB versus CSK match. So you know for sure that whatever input the lower neuron gives, because it's talking about RCB versus CSK, it has to have a higher weight, right? So exactly how do we keep track of weights intuitively? In this diagram, each circle, as I said, is a neuron, right? And each of these black connection lines, you can imagine the weight to be along that line, right? So like in your brain, neurons are connected. When they're connected, what flows is basically a small electric current, right? So let's say we have that kind of current here. It's originating at this neuron and it's traveling along this line to this neuron. Same way, it's like that. So just imagine that the data flows along these lines, and along each line, it encounters what is called the weight. And this weight basically determines how important a particular data point is to each of these neurons. So for each of these neurons, you can say that if this represents the RCB versus CSK, the lower one, we know that the lower neuron's input is more important than the upper one, right? So if I take this uppermost blue neuron, for example, I can see that all the black lines that originate from the black line that originates from the lower neuron in the input layer has to have a higher weight than the upper ones, right? So that's what a weight is. And then what's a bias? So a bias is a concept that I'm not sure if you've seen so far, but a bias is basically each neuron has an inherent it adds a value inherently. Like so for example, this neuron might add some value to whatever output it's generating. So that's called a bias. So it is what its name implies basically, because each neuron feels that it has a certain bias towards a particular output, so it tries to adjust to that output, right? So we'll be coming into mathematically what is a bias. We'll be seeing that soon. But so intuitively, a weight decides the prominence of a particular edge, and a bias is the inherent property of a neuron, right? So I've not shown biases as such, but you can just remember, keep in mind that each of these neurons has a bias of its own, right? Which it will add to the input. Okay, so here there is one thing that we are ignoring, and that is the bias of this input here. Okay, because we are simply assuming that this layer does not, because it's an input layer and it should ideally not be changing the input that you give. So this layer it's alone does not have any biases. The other three do. And when I say blue underscore weights, what do I mean? Here I mean the weights on the lines that terminate at the blue, right? So these lines basically, these ones that end at a blue neuron. So all of these lines come under blue underscore weights. All of these lines that connect blue to orange come under orange underscore weights. And these lines come under yellow underscore weights, right? So that's another thing to keep in mind. So there is these two points to keep in mind. Of course, you could have named it differently. I just chose this kind of nomenclature. There's no fixed way of naming them. And then I'm using this function called torch.rand. So if you remember, when he did Perceptron, Ritwik took specific weights, correct? He hard coded some weights. So instead of doing that, because we are using PyTorch, right? Because he wasn't using PyTorch, he did that, but we are using PyTorch. So we have the advantage of using this function called torch.rand. So what does torch.rand actually do? It generates a random array of whatever size you ask it to. So 3 by 2 is basically a three dimensional, three rows and two columns array. Same way 3 by 3 is three rows and three columns, like that. So when I talk about this torch.rand, how did I choose these numbers? So that's something we need to look at. So what exactly does 3 by 2, 3 comma 2 imply here? So if we look at this here, let's see. So the standard way of naming the weight tensors, deciding the shape of the weight tensors is, if you say it's x comma y, then what is x? The number of neurons in the layer that it connects to. And what is y? The number of neurons in the preceding layer, right? So the weight, as I said, lies in each of these connections, correct? So each of these connections carries a weight, and it terminates at a layer that has three neurons. It starts from a layer that has two neurons. So it's 3 comma 2. Similarly, if I talk about these lines, remember I'm calling them orange weights. So these orange weights will have, okay, so they are terminating at something, a layer that has three neurons, and they're originating at a layer that has three neurons. So it's 3 comma 3. Similarly, it's this one here, yellow weights, they terminate at a layer having one neuron, and they start at a layer having three neurons. So it's going to be 1 comma 3. So let's see that. See? So this is 3 comma 2, this is 3 comma 3, and this is 1 comma 3 using this nomenclature, correct? And there's this other parameter requires underscore grad equal to true. So I'll be coming back to this in a while. This will be used for what is called gradient descent, which is actually how the model itself learns. So we'll be looking at that in a little more detail soon. So let's not worry about that for now. For now, what you need to know is basically we've generated arrays of an array filled with random numbers of a specific size. And how did we decide the size? Based on the number of neurons in the layer at which the weight terminates, comma, number of neurons in the layer where it originates. Okay. And then we have biases. So a bias is for each particular layer, right? So what does 1 comma 3 actually mean? When I talk about the blue biases, 1 comma 3, so this the way you decide the size of the bias layer, you know that there has to be something that is based on the number of neurons, right? So there are three neurons in this, that's why there's three. Similarly, the orange bias will have three, and the yellow bias will have one. And the preceding is one because there is actually only one layer of three neurons which you have to worry about when you talk about blue biases, right? So you don't worry about, unlike the weights. The weights were connecting two different layers, but biases are not connecting anything. Bias is something that is only for this layer or this layer or this layer separately, right? For each neuron in those layers. So it's 1 comma 3, 1 comma 3, and 1 comma 1. So we define the biases using the same torch.rand. Again, requires gradient. We'll be talking about this soon. And we also defined an input that again is random. So you must be wondering why the input is random. The input is simply random because, of course, every time you run this code over and over again, it's going to change because it's a random tensor. But for any layer, we just want to see if the model works. So it doesn't matter. So we just decided that, and why we'll be using torch.rand. And why have I done 1 comma 2? again, we're talking about one layer in which there are two input neurons. So basically 1 comma 2 implies that, in a single row, I have two columns, each column indicating a particular neuron, right? So we just let's just run these cells as well. So you won't actually be able to see any outputs here, but you could if you want to using print. I did not put them there so that there's no confusion. Okay. Any doubts so far before we move ahead? Is there something in the chat? Okay. No doubts. All right. So let's move ahead. So now we come to forward pass. As I said, forward pass is basically just the output. So, okay. So this is a part of the network basically where the output value is calculated. And so if you remember from when when the perceptron was discussed, right? Uh, like right after that, there was the diagram of the neural network where we said it's basically the summation of weights times input plus bias. Okay, so that's what I've written here. So it's weight times input plus bias is the output that should come from each neuron. But there is also something called the activation function, right? A function that each neuron applies to whatever value it calculates, this input times weight plus bias. This is then passed into a function, and whatever value comes out of that function is the final output from each of these neurons, right? So this is basically called forward pass, where we are finding the output. So we see that if we had to do it without using tensors, then we would have to do this multiplication separately for each neuron, sit and add it manually. So you see the power of PyTorch lies in this. You don't actually need to do that because you're allowed matrix multiplication. So these arrays are basically matrices, and we can do matrix multiplication, correct? So I'm defining this forward function here. So it's taking an input, whatever input it's getting, weights and biases, and it's calculating the output as I have written here. Inputs times weight plus bias. So the symbol, this at the rate symbol, basically tells PyTorch that you need to do a matrix multiplication. And why is it weights dot t? So dot t basically does transpose. So weights dot t is basically taking this weights there and taking the transpose of that. So you must be wondering why we have to do this. So let's look at this blue layer. Let's say. So we're getting in the input layer. That's the input we're getting is of size 1 comma 2. So one row, two columns, correct? And the weights for that layer are here 3 comma 2. Okay. So if we want to do the matrix multiplication of input versus weights, so we know intuitively what kind of multiplication should happen, right? You're taking each input, you're multiplying it with the weight of the corresponding line that's bringing that input into each neuron, and you're adding the corresponding weight bias. But how do we tell the computer that? The computer can only understand matrix multiplication. So we know that for matrix multiplication, the sizes have to be appropriate, correct? So 1 comma 2 and 3 comma 2 cannot be multiplied directly because the columns of the first matrix has to equal the rows of the second matrix. So since input times weight, this is the first matrix. So we have this of size 1 comma 2. So instead of 3 comma 2, we want this to be 2 comma 3. So we take the transpose of it. So dot t basically takes the transpose of a matrix. And then we're doing here. What does this torch dot redo mean? So this is where we'll be getting a little bit into activation function. So let's go into that. So this is basically what activation function is. The activation function is a function applied at each neuron on that weights times input plus bias to get the final output of that neuron. So what exactly is a ReLU activation? So ReLU stands for rectified linear unit. Again, not too important. But what you need to know exactly is what this function is. So this function is very simple. If my number is negative, it gives me 0. If my number is positive, it gives me the number back, right? So this is exactly the graph of ReLU. Again, this is I've just put this here for reference. You don't actually need to get into this. You just need to know what this function does. This function gives me back my number if it's greater than 0, or it simply gives me 0 if it is a negative number, correct? And then there's a other activation called sigmoid. So sigmoid, as Ritvik had said, is 1 by 1 plus e power minus x. So it's just a function like this. The implications of this function you'll understand in later sessions. This is actually related to probability, but for our purpose, it's not very important. What we need to know is that these two are functions that a neuron can apply on this value to get a final output, correct? And we'll be using these two activations basically, ReLU and sigmoid. So now I'll be coming back to where I had said this. We'll use ReLU activation for these layers, and we'll be using sigmoid for this layer. Okay, I've just taken it this way. You could have taken it anyway. You could have taken it sigmoid for all of them, ReLU for all of them. It doesn't matter. I've only taken it this way for to show, to give you to just show that both of these can be used. But otherwise, you can use it either way. Okay. So I'm using, so here where I had found weights, I've reached input times weight plus bias. And now I want to apply ReLU on this. So I use this function called torch.ReLU. It's very straightforward. Torch.ReLU basically it's a function that's inbuilt in PyTorch, and it applies this ReLU function to this output. So if this value here. Okay, so you must be wondering what it means to apply a function on a matrix. It's not actually applying the function on the whole matrix. Torch dot see this is the advantage of using PyTorch is each of the functions is built keeping in mind that you'll be giving it a matrix, correct? A tensor. So it applies this ReLU activation on each element of this tensor. So if each of these elements, every element that's greater than 0 remains as it is, every element that's less than 0 simply becomes 0. So that's what this does. And then you're returning this output. So running this will of course do nothing because as of now we've not actually called this. And one more thing you realize is that I've used ReLU in the definition of this function itself. But we also know that this layer cannot do ReLU, right? We wanted to do sigmoid here. So I just code that separately every time we need it. Ideally, if you're reusing them multiple times, then you should code two different functions. But in our purpose, since it's just one neuron where we have to show that sigmoid activation, I'm not doing that. I just code it separately for simplicity. Okay. So what does blue underscore forward mean? So the forward pass of this blue layer is what I'm finding by calling this function. So for the blue layer, when I give the inputs from this red layer, I'm giving the inputs to this blue layer, and I want to know what data is being transferred along these lines, all of these lines. So this will be stored in some matrix, right? Using this input times weight plus bias, and then applying ReLU activation on each and every single element of that matrix. So this is exactly what blue underscore forward will hold. The same way orange underscore forward will hold the forward pass of the orange layer. And when we come to the yellow layer's output, you need to be careful. In yellow layer, we can't just call this function because we want sigmoid. So basically, you do this and then you do torch.sigmoid of that. Now, one crucial aspect here is to understand the power of neural networks. What exactly is the input for this layer? So the input of this layer is the output of the preceding layer. And this is actually one of the major things in a neural network because it's interconnected, data is fed into it and it keeps getting transferred with various optimizations and functions until you get an output. And this is actually where all the prediction work happens. This is what, as you will see in some time, this is exactly what we'll be training to optimize this output. Okay, so we'll be seeing that later. But the important point is the output of the preceding layer is going to be the input for the next layer because it's sequential, correct? That's the whole definition of a neural network. It's a sequential layers of neurons. So we'll be finding the forward pass of the yellow layer by taking the output of the orange layer, which was the preceding layer, as you can see here, multiplying it with the weights of this layer. Okay, so it's not actually weights, it's only going to be one weight, but yes. And then we'll add the bias of that. And then we use sigmoid activation on this to get the forward pass of the yellow layer. So you can see from the diagram that forward pass of yellow layer is nothing but the output of the entire model, right? So this is exactly what we get from yellow underscore forward. Again, running this because I have not written any print statements, it's not going to do anything, but we can always try see. Sorry. Let's say I try to print the forward pass of the blue layer. Okay, so we see this is the output, right? So it's a two-dimensional tensor with three values. So you can see that each of these basically has three outputs. So we get that. This is basically how the forward pass works. So let me just run that again. Okay. Any doubts so far? There's something on the chat. Any doubts? Also, is the pace fine or should I slow down? Because we'll be getting into the more crucial part soon. So please give me some feedback on that. If needed, I'll slow down because that's the part where like we'll be seeing learning, deep learning. We actually be seeing the learning part. Um, can somebody from the audience please give me a feedback?
Little bit
Just
slow
want
down,
to.
sir.
Sorry.
Can you little bit slow down, sir?
Okay, sure. I'll slow down. And any other doubts so far up till forward pass? Okay, I take that as a no. So fine. Yes, I slow down. Thanks for that. Okay, this part is fairly trivial. So I've found what the true value should be. So if you remember, right from the very beginning, right from McCulloch's neuron, we always have a predicted value and we have a true value, right? So similarly, we'll be needing true values as well. So again, I'm using torch.rand. So again, you might be wondering how can the true value be a random value,
Srinivasan.
correct? Yeah.
Yeah, there is a doubt in the chat, bro. I guess you can take that up now.
Okay. Which is better to define or not define a separate function for sigmoid and ReLU? Right. So in our case, because we have only one layer that uses sigmoid, correct? That's why I did not define a specific function for it. But if you have multiple layers that are using sigmoid, then it's always better to define. So the use of a function is to avoid repetitive code, correct? So you can keep calling the same function and apply it. So it is better to write a separate function if you have multiple layers using it. Always good practice. Okay. And can you explain biases once again? Okay. So what does the word bias mean? So when you say you have a bias, suppose we're in a courtroom and you say the judge has a bias. So what does that mean? The judge has already in his mind, he has some favoritism, you could say, towards a particular, turnout, right? Either guilty or not guilty. He already has something in his mind. Like he feels, okay, this guy, he looks innocent, right? He's wearing good clothes or something. He speaks in a polite manner. He's being nice to me, so I'll be nice to him. So he has a bias to prove him not guilty, correct? So that's called bias. When you already have a notion of what you want something to be, that's called a bias, correct? And that is exactly what biases are even here. So this orange layer, right? Every neuron has some bias. It's say this has some x value, some y value, and some z value, correct? So this thing basically it already has an inclination to add its own value x to any output it makes, right? It feels like, okay, everything I'm getting should be at least this value more. this field, it should be everything every output I'm generating should be some y value more. This is saying every value should be some z value more. So this is where biases come from. And this bias is okay, of course, in a real life scenario, a bias is normally something you cannot actually change, correct? But we see that in neural networks, the bias can also be trained, right? So that's basically what bias means. Bias is what uniquely defines each neuron in the layer, you could say. That what is the difference between this and this and this? Like if all of them are just doing input times weights plus bias, so it, I mean, it may or may not be different, correct? But what is the individuality of each neuron? It's the bias. Mahendra, is that fine? It's basically just a value that each neuron adds to the output to compete what it feels should be the output. Uh, okay, cool. So we were talking about true values. So as I said, we basically want true values. So I've defined again random tensors, and now how did I get this size? Let's have a look at that. Now, when I'm talking about the blue layer's true values, I don't care about the preceding layers. I don't care about any layers after it. I only care about this layer, right? So my rows defines the number of layers I'm worried about. So I have one layer here, and three columns means three neurons. Similarly for this, it's going to be again 1 comma 3 because there are three neurons and I'm only worried about one layer. And this should have 1 by 1 because I'm only worried about one layer and there's only one neuron in that layer. Correct? So this is how we decided the sizes. So again, running this, I have not given any output statement, so it's not good. So requires underscore grad. For now, let's not look at it. We'll be looking at it soon. Okay, coming to the loss function. All right. So a loss or a cost function is what allows us to get a metric of how our model is performing. So how do we know if it's performing correctly or not? Like how do I know it's predicting correctly or it's not predicting correctly? So I have to compare the true value and what it's predicting to get a sense of how it's performing. And we do this using what's called a cost or a loss function. Correct? So there are many types of losses. So I've given, like, broadly we categorize into two parts. One is a regression and classification loss, and another is called cross entropy. So like, don't get intimidated by this big formula here. We won't be dealing with cross entropy loss. It's just good to know that it is a useful type of loss that will be used in later sessions possibly. But I've just given the formula here for the sake of completion. Let's not worry about this. What we'll be using is this mean squared error loss, right? MSE. So this is what even Ritvik had used in the Perceptron, if you remember. So here the loss is simply okay. What for each neuron, I'm going to look at what value it's giving me, what value it should give me, square the difference, and sum them all up. So that's giving me the total thing. And then divided by the number of neurons. So that will give me a mean. That's why it's mean squared error. What? So E stands for error. So that comes from the difference between the true value and the predicted value. Square comes from because we're squaring each of these values so that we don't have the minus or plus issues basically. And we're taking a mean of that. And that's giving me a final number that we're considering as the MSE loss. Okay, so this is the value, this is the MSE, and this is basically the mean squared error. Okay, so sorry, this is just the squared error. My bad. Okay, so this is just the squared error. To get it as MSE, we need to take the mean as well, which I've done here, right? So if we talk about the losses in the blue layer, I'm looking at the forward pass is what, if you remember, gave me the output. And I also defined a true value. So if I subtract these two, I'm going to get the error, right? So I've subtracted them, I'm getting the error. And if I square it, I'm getting the squared error. And again, the usefulness of PyTorch comes in here. If you are using normal Python this, then what would you have had to do? You would have to write some loop you'll have to find each element in that array, add them all separately, and then take the mean. So PyTorch saves us all the trouble. There's an inbuilt function called torch.mean, which simply finds the mean value of all the elements in that matrix. So when I do this, blue forward minus blue true output, I'm getting the error, I'm squaring that, and I'm taking the mean. So I've got the mean squared error in blue loss. Similarly, I've done it for orange and yellow layers as the loss. So out of this, which one do you think is the loss value that truly matters? If we consider this whole model, let's say this thing is in some machine and it is going to perform some function for us in which we are simply giving the input and the output. So which can you guys guess which loss function, which loss value actually holds meaning? Any guesses? Right. So I just repeat the question just in case. See, sorry.
The mean squared error
Uh,
loss.
someone saying something? Yeah, it's mean
Yes, I
squared error
was.
loss. What I'm saying is, uh, I found losses for these three different layers, right? One is a blue layer loss, one is an orange layer loss, and one is yellow. So which one should I actually be worrying about most? Right. So when you actually run something, you're interested in the final output, correct? Uh, no, not really. See, so the idea is basically I'm getting my output from this yellow layer, right? So I am actually more interested in how well this yellow layer is giving me the output, right? Fine, I get it. The inside, let's say the blue layer, you know, overestimates the value. The orange layer underestimates the value, right? But everything is fine as long as the yellow layer gets it correct, correct? Because this is where I'm taking the output from. Suppose this was 100, like, let's say we're finding some stock price. Let's say we're trying to predict some stock price. The blue layer says the stock price is 100 rupees more than it is. The orange layer says it's 100 rupees less than it is. But it could well be that the yellow layer gives me the exact stock price, correct? Right. So we'll be worried about the layer where we're taking the output from, because even if the hidden layers get it wrong, if put together they get it correct, then everything is fine. Correct. So we'll be focusing more on the loss of this yellow layer, because this is the output layer, and the final output is what we generally worry about when we're talking about practical situations. Right. So I just run this. I've just found the different losses to give you a better idea of how it's found. But going ahead, this yellow loss is what is the most important part to us. Okay. Any doubts so far? Feel free to unmute or drop it in the chat box. Either way. Okay. So uh, I guess no issues. So let's move on into the interesting part. So there's this function that we need to explore a little bit before we get there. Okay. So I'm going to take this function torch.grad. It's a pretty useful function, and it basically gives us the gradient that we want. Gradient as in slope, right? So let's take this polynomial y equal to x squared plus 3x plus 5. So what's the differentiation of this? 2x plus 3, correct? So the differentiation of this function will be 2x plus 3. So I just write that there. So dy by dx is 2x plus 3. Okay. So let's say I have some input x equal to torch dot run 1. So what does 1 mean? It's just one value, one number. If I run this, I'll get a single number for x. So let's just run that and see. You'll notice. Okay, this is just one number 0.4108, right? It's some random number because this is torch dot run, correct? So every time I run it, it's just going to be some different number. Doesn't matter. Now I'll be talking about what this requires grad equal to true mean. So requires grad equal to true is basically it's keeping track of which of these values is the variable, right? So if you remember, so here dy by dx, x is the variable, correct? X is a variable input and y's gradient depends on x. That's why I've said requires grad equal to true. Because keeping in mind what my final function is, whatever variables define this function, I want to be able to get gradients with respect to them. So that's what requires grad equal to true mean. Now the name is a little bit it might be a little bit counterintuitive. Requires grad equal to true doesn't mean that x's gradient is we require a gradient for x. No, we require a gradient for something else with respect to x. That's what requires grad equal to 2 means. So now if we go back through the code from the very beginning, there were multiple places where we'd use this variable. So weights and biases, as I said, are the trainable parts of the code, correct? So if I want to train these, I should be able to get gradients with respect to this. Like why this is so, it'll be clear later. But here in all the weights and bias tensors, I've said requires grad is true, which means I'll be finding the gradient of something with respect to these. What that is, we'll come back to soon. Okay. Whereas the input and the true values, if you see, the true values and the input, these are all set to false because these are for like if I for any given run, this input is going to be a constant. The true values are going to be constants. They're not going to change. So I don't actually have to train them. So I don't need gradients with respect to them. Now you might be wondering why if something is trainable, you need a gradient. So I'll be coming to that soon. That's actually what gradient descent is about. But for now, we just need to understand what this requires grad equal to true means. It means that I can find the gradient of something with respect to x. So if you see when I print x, it automatically prints this requires grad equal to true. So PyTorch is keeping track that okay, x is something that can vary. Okay, so I printed x, and now I've defined y. Y is exactly what I've defined here: x square plus 3x plus 5. So dy by dx is 2x plus 3. Y dot backward. So what y dot backward does is so it starts looking at everything that y depends on, all the variables that y depends on. So y depends here only on x, but it could very well be something like this, right? It could be plus z, right? Plus k, let's say, plus l. Like all any of these could be variables. So what dot backward does is it starts looking, okay, y depends on, let's say, some variables. So I start calculating the gradients with respect to those variables. That's what y dot backward does. Y dot backward has already found dy by dx. And if it was suppose z, then it has already found dy by dz. Suppose it is plus k square, let's say something. Then it has already found dy by dk plus some j. It's already found dy by dj. Similarly, it's found for all the variables that you have set this requires grad equal to true for. In our case, there's only one, there's x, right? So for us, it's already found dy by dx, and it's only found that because I've set x as requires grad equal to true. And when I say print x dot grad, it means that I want dy by dx. So what would it have been? Suppose I wanted, let's suppose this was this z. So y dot backward, it found dy by dx. It also found dy by dz, right? So now if I want dy by dx, then I print x dot grad. If I want dy by dz, I would have printed z dot grad. So this is the basic functionality of this function. You just need to know how it's defined, right? So I've said this here. So you can see, you can try it out for yourself. You see 2x plus 3. Substitute this value of x, and you see that 2 times this plus 3 gives you this value, 4.5338. Right? So it found dy by dx. Now suppose I had set this to false. Let's see what happens. I'm saying that, okay, I don't want x to be a variable at all. Then you see it raises an error. So why does it raise an error? Because it does not have anything, like whatever it depends on does not have a gradient associated at all. Like there is no dx for dy by dx. So this function raises an issue. Correct? So I'll just set this to true. I think that gives you an idea of what this grad does and what dot backward does. Dot backward starts the process of calculation, and x dot grad tells it to give you the dy by dx from that. Okay. Now we'll be getting into what gradient descent is. So gradient descent is basically, okay, whatever I did with y here, I want to do with my loss function. Why do I want to do that? So our loss function is some quadratic thing, right? So let us say this is the graph of that cost function, hypothetically speaking. So I want to know where the minima of this loss is. Because if my loss is high, it means that my prediction is wrong. Correct? The higher my loss, the more wrong my prediction. So I want it to be as correct as possible. And for that, my error has to be minimum. The error is the loss function. So I want the loss to be minimum. So I want to find the weights and biases such that I hit this minimum. And that is basically the process of gradient descent. Finding the weights and biases so that you hit the minima of the loss function. So for this, I found d of loss upon d of weight or bias. Okay, because I want to know how this loss function changes with each of these weights. In our case, the loss function will change based on the weights of this year. It will change based on these weights. It will change based on these weights. It will change on everything, right? So I want to know how it changes, and accordingly, I want to update it. So that was this. That's what we're trying to do here. And obviously for this part, I'll be using this function because I want the gradient, correct? So the details of gradient descent and backpropagation, actually you will learn more about on Monday, the mathematical part. But for now, what you need to know is I'm trying to update weights and biases so that my loss decreases. This is the goal of what we're trying to do here, correct? And we see that this code, right? So what is the code? As I said, okay, there are actually a few important things to note here. I've done yellow loss dot backward. So why am I finding the gradients for yellow loss? As I said, it doesn't matter. Suppose these layers are wrong, but this layer is correct. This is all that matters to me. So this is the loss which I want to minimize, right? That is why I'd asked that specific question on which loss we want to minimize, because this is the loss that we are actually interested in minimizing, the yellow layer, right? So I've taken the yellow loss and I've done a dot backward. What this does is, okay, it looks back all the variables that I defined as requires grad as, okay, so not here, requires grad as true. It starts looking at the dependency of this yellow loss. Where's that yellow loss? Yeah. So here you might be thinking, okay, it depends on the true output, which doesn't require a gradient, and it depends on the forward of the yellow layer. Now let's look at the forward of the yellow layer. The forward of the yellow layer depends on the forward of the orange layer, yellow weights, yellow biases. Orange forward again depends on orange weights, the blue forward, and the blue, the orange biases. So you see, the final output has a dependency on all the weights and biases of all the preceding layers. So that is what is important. If we were to do this manually, it would take, like, for this year, for this network, we might still be able to do it manually. It will take a while, but we'll be able to do it. Suppose I had 100 search layers. It is not possible to do this manually. So that is why PyTorch is very powerful, right? Because PyTorch does all of this for us. You see, I did yellow loss dot backward. It automatically calculated D of this loss, D of yellow loss, upon D of every weight and bias of all the preceding layers, and that's the main that's the crux of this part of the code. Okay. Why this works, you'll be, as I said, you'll be looking more at once on Monday, where we'll be taking up actual details of gradient descent and backpropagation. Right. So then I've started updating the weights. So this formula yellow weights equal to yellow weights minus 0.01 times yellow weights dot grad. Let's look at this one. Okay, because we figure out this one, we'll be able to get all of the others. So 0.01. First of all, what is 0.01? 0.01 is called a learning rate. If I put my learning rate as 0, the weights do not update at all. It basically means the model does not learn at all. The higher my learning rate, the faster the model learns. But you must be wondering why I've kept it as such a small number then. Like, why 0.01? It could easily be a bigger number, correct? If I had kept it as 10 or 100, it might be learning faster. But no, that's not the way it works. Because you see, what am I doing here? In this graph, if my y value is the loss and the x value, let us say, is the weight, right? So if I look as per this function, what am I trying to do? I'm trying to decrease my x value to minimize the loss, correct? And this x value, it depends on both the gradient and this step value, correct, which is called the learning rate. Now if my learning rate is 10, and suppose I'm here at this blue point, let's say I'm here, and 10 times this number actually ends up being much bigger than this x value. So it will bring me to the negative. So what did I do? I overshot this minima. Overshooting the minima is as bad as, staying where you are, correct? I mean, it could very well be that just because you overshot the minima doesn't mean your accuracy is going to increase. It could very well be that it decreases. Like if I multiply this by 1,000, and this is some, let's say this is some value x, it could easily be that I reached much further away on the negative side, in which case the model became even more useless, correct? So that's the issue with a very high learning rate. On the other hand, a very low learning rate, you might take a long time to reach this point, correct? Like, I mean, if you're just increasing in 0.00000001, then I'm inching closer and closer, but it will take so many iterations that it is possible the computer won't be able to do it. So that is why this deciding the learning rate is often a very important part of training any neural network. It's not very easy to find this learning rate, and many times it's just trial and error. But it, like, for many of the models that we encounter, 0.01 is a sweet spot. It's neither too fast nor too slow, so we tend to use 0.01. And yellow weights dot grad is basically finding d of yellow loss upon d of yellow weights, multiplying that with 0.01 and subtracting it from the weights. Why the subtracting? Let's look here. As I said, the weights are going to be the x values, correct? So suppose I'm here at this point of time, I'm here at this point of tangency, I'm at this x value, and I want to move in this direction, and this slope is positive. So if I have any number times this, like this positive number, what should I do, add or subtract this positive number from the current value of x to get closer to 0? So for positive x, I need to subtract it. For negative x, where the slope itself becomes negative, I need to add it. So if I'm here, subtracting this positive number will bring me closer to the origin. If I'm here, adding this, adding the positive value, like, how do I put it? Subtracting this negative value in a way is basically adding a positive number, correct? So if you add a positive number to a negative number, you're bringing it closer to 0. So you can see that, uh, intuitively speaking, the minus sign is correct, because if it had been a plus, then from here I'm just going to end up going here. I'm going to go here. I'm going to get further and further away from the minima, which means my model is more and more useless, correct? So that's why the minus sign is there. And exactly why we are doing this is something that you'll be able to understand in greater detail on Monday, right? For now, uh, just trust me that this is how you train it, correct? This is how you update the weights and biases. Again, why it's like that, you'll be able to see more on Monday, correct? Okay, so, and then the final part is basically I printed the earlier loss. I found a new loss by running the entire forward propagation again. And if I print them side by side, you see that before I updated the weights, it was this value 0.5682. And after I updated the weights, it became 0.5680. It may not seem like much, but I mean, if you look at it, it's already a number less than 1. So for that, this is a pretty good decrease, right? So the decrease in the loss means that we have managed to train our model, correct? Because it's learned something, and that is why the weights and biases are adjusted accordingly, and it brought it closer and closer to the minimum. So that's basically how the neural network works. The like, any questions so far? If not, I'll give a briefer, a better idea of how that gradient descent works. A little bit more. Any doubts? So another thing is it might be overwhelming to see so many different functions, but don't worry. Anyways, you can like the syntax is never important. What you want to do is important because like PyTorch will basically offer you anything that you want to do. So you can see that I've compiled the functions that we've used today, exactly what they do with their syntax. But otherwise, as I said, don't focus on the syntax. It's more important to understand how these things work, like exactly how it's like doing what it's doing. Like why is it able to find this loss? Right? What is torch dot mean doing is not as important as that you need to find the mean here. Any doubts so far? Okay, so since we have a little bit of time, um, it will help to understand what we are doing. So like this is a part where it's going to get a little bit mathematical, but not much. Uh, if I want to like change something, let us say I want to move along this line further down. Okay, like if you remember from calculus, the approximate value of something is the value plus or minus derivative like dy by dx. Oops, sorry. Just a second. Yeah, plus or minus dy by dx times delta x, right? So let me let me just, so I have delta y equal to y plus or minus dy by dx delta x. So uh, anybody who's not familiar with this, anybody who's not exactly familiar with how this works, like if so, please tell me. I'll explain it a bit more. Okay, I guess everybody knows this formula, right? So delta y equal to whatever value of y you are at plus or minus dy by dx delta x. So I mean, obviously, I can flip this around, correct? Like for x as well, I can say the same thing. So that's exactly what I want here. That is why it works as well as it's working, right? So because I want to look at this x value and I want to move it in a step down this path. So if I'm at some value of x, I want x minus dy by dx times this whatever the step value is. Now for this formula it worked. Delta y equal to y plus minus dy by dx delta x. This works. But when I'm talking delta x, right, it's not necessary that I know what that is. So I'm avoiding the confusion of exactly where we are and stuff like that. Instead, I'm saying it's just y minus, you know, times some parameter, and this parameter is called the step size, that is the learning rate. So if I multiply the learning rate times the gradient, it basically tells me how much I'm supposed to move, and the x minus that basically means I'm moving that much along it. So that's basically the goal of gradient descent. The mathematical details and like a little more intuitive understanding you'll get on Monday, as I said. But I hope this gives an idea of exactly why we are doing this. And yeah, basic point is that the loss value should decrease, and that's happening. Any questions? Okay, so that's about it. So if you guys have any doubts or clarifications or anything, please tell us. Otherwise, I guess we call it a day.
Understood, sir.
Okay, cool. Thanks. So I hope that worked. I've like I guess the notebook and the slides have been put up on the group, and they're also up on our repository. So you can always look back to that. As I said, the slides are more of a the sites basically serve the purpose of compiling all the functions and giving a basic idea of what cost and the definitions of the activation functions are. The more important part, I guess, from today's session is the notebook where we learn to code it. As I said, don't stress over the syntax. Right? The syntax will only come with practice. It's not something that you necessarily remember the first time you do it. And plus, you can always Google it up or something. The more important part is what we are trying to do, why we did, like how we found that output that we had found, input times weights plus bias, uh, what a weight is, what a bias is, and that we are updating those and which loss we are trying to decrease. Like these intuitive aspects are the more important part. So let's focus on that a little bit more. Don't get discouraged looking at big code. I mean, generally the code might be big, but really once you understand what to do, even you can write such big code yourself. So it's fine. I have also attached a further reference. It's like on PyTorch linear layers. That's something that uh, you can have a look at. It's basically a useful tool that PyTorch offers us to just write an entire layer in a single line of code. So that will be more useful when you're dealing with hundreds or thousands of layers. Like if you have too many layers, then you can't do it manually. So yeah, I mean, more layers you can always use that. Okay, thank you. Dave, you there? I guess can end the meet, right?
Yeah, Dev. I guess you can end the meet.
Dave, are you there?
Yeah, yeah. Am I audible?
Yeah, yeah.
Yeah, you
I
are.
think we're done. So you can end the meet. Yeah.
Yeah, I guess. Yeah, that concludes the meeting. Bye, guys.
Thank you. Bye.